Thank you, Peter. And good afternoon. And my name is Li Guo. Oh, hello? Okay, sorry about that. Good afternoon. My name is Li Guo. I would like to thank you for attending the ARB's joint seminar on nitrous oxide emissions from agricultural soils. And today's seminar will offer an opportunity in an open panel discussion to interact with the investigators and also provide feedback on our research program. I will start by introducing our three speakers. We'll also provide a brief overview of this topic. In 2008, ARB initiated a research program to determine nitrous oxide or N2O emission rates from agricultural soils in California. The program was coordinated with three other state agencies: California Energy Commission, California Department of Food and Agriculture, and the California Department of Resources, Recycling and Recovery. Today's seminar will present results of the field studies on nitrous oxide emissions conducted by the three research groups from University of California, Davis, and the California State University, Fresno. And the first presentation.
So it confirmed actually that it was really the cover crop that was pumping out, that was leading to that nitrous oxide coming out in the vineyards. So that's for the vineyards. Then we went over to some processing tomatoes. And here it's that these systems here before, I was basically just showing you, what are the emissions, business as usual. Nothing has changed. It's just whatever the farmer is doing. Here in the processing tomato, then we wanted to look at how is that, how can we have some other system that actually might help with reducing the emissions. So we had on the one hand a conventional system, so the conventional tillage, we had furrow irrigation, and so because of the furrow irrigation, we rip and reform the beds every year. And so that was basically our typical processing tomato system. In the integrated system, which is the farmer that we worked with actually had devised this. This is nothing that we came up with. The farmer himself actually figured out, okay, I want to try this, I want to do this. And he has done it actually already for many years. So I'm not giving here a best management option that I dreamed up. Sometimes I get to hear that I'm an ivory tower scientist, and so I dream up things that don't have anything to do with what's happening in the field. This is what the farmer dreamed up, not me. So don't tell me it's an unrealistic system. I guess that's what I'm saying. Reduced tillage, subsurface drip irrigation. He puts in a winter grain cover crop so that he can actually keep that bed aerated, and then because he is indeed preserving that planting bed. He's not ripping it and reforming it. Okay? So that's a system that he came up with. I'm showing you the furrow versus the side versus the berm, because in a system like that, obviously we knew from the beginning on that the emissions would be quite different in those three different locations. Because in your conventional system, the water is coming mostly from the furrow. In your integrated system, it's all coming from the drip line that's under the berm. So the water dynamics are quite different across those three different locations within the field. And so here are the results. So if we look then at the different events, so we have a bunch of fertilizations, we have some irrigation things, and what I'm showing there is basically an average of several irrigation events. We have the harvest, and then we have the first rains. And so what you see is in the conventional system, we have, with the fertilization, actually quite high peaks coming out of N2O. At harvest, we have one also, but also in the integrated system. And then with the first rains, we see again an emission happening in the conventional, also in the integrated, but not as much as in the conventional. And so we clearly see indeed that fertilization, that furrow fertilization in essence in the conventional is actually leading to quite a bit of nitrous oxide fluxes. And so when we look indeed across the different locations in the conventional system, what we see is that most of the emissions are coming from the side and the furrow, so where we're adding in the fertilizer with that water. So you're having your moisture, you're having your nitrate, and there's obviously enough, there's enough carbon, and so it gets pumping. In the integrated system, we have across the tree actually quite a bit less fluxes. So we're reducing it quite a bit. And I have to say, this was much more of a reduction than I had ever dared to dream that we would see. And so if you bring it indeed all together across all 3 locations, your conventional system, we're sitting at about 2 kilograms per hectare. For the integrated system, about 0.6. And so we basically have about 2/3 of a reduction in nitrous oxide fluxes by that integrated system versus the conventional system. Now that's all fine. The good part is that in the integrated system, we're adding maybe a little bit less fertilizer because we're actually using it, we're doing it through the drip more often, so we don't have to add quite as much. But your nitrogen use efficiency is quite a bit higher, and we actually have quite a bit more yield in that integrated system compared to the conventional system. So we're still having the yield, and we're able to reduce that nitrous oxide. So we're basically having a double deal going on here. No reduction in the yield, if anything, actually an increase in the yield, and we are having less of an environmental impact via nitrous oxide. In a last project I want to show you is where we're looking at how biochar, and I'm sure all of you have heard in the last few months, year, a lot about biochar because it seems to be the hype of these days. And so what we did here actually was kind of working with a farmer that, well, not kind of, we were working with a farmer that had already a system set up. Namely, he's a walnut farmer, and he also processes a lot of the walnuts from his neighboring farmers, all organic. Okay, not that that's of importance, but it happens to be an organic farmer. So he gets all these walnut shells, all these walnuts from his neighbors and his own orchard, processes them, and then he sits with a mountain of walnut shells. And it is really a mountain. I suggested several times to the farmer that I would come out and ski ones down it because it is actually really, it was pretty high. But he had found a solution to that mountain. Namely, he bought this gasifier here, this Biomax, and it's basically a pyrolysis unit in which he can bring in the walnut shells, then burns it, gasifies it, and what he gets out of it is heat and electricity through a generator. There is actually a little tap on the side where you can get out some biofuels, not too much, but there's some that comes out. And then you come out and you have some biochar. Not all of that walnut is burning. There is some ash, basically, that's left over. And so the question was, well, what am I going to do with this? Because he reduced his mountain of walnuts. But it's still about 1% of the carbon that you put in that gasifier comes out as biochar. So he has several tons of biochar lying around at the moment. So what are we going to do with that? That was the question. And so what we wanted to look at then is on how that biochar might be able to, several people had suggested that nitrous oxide emissions could be reduced by amendment of biochar. When we did some little experiments, what we saw, okay, we have the no amendment and we have indeed that char ash that has been added. We see a bit of a reduction, but I wouldn't say that I'm jumping up from excitement because it's hardly ever, it's hardly a reduction. It's not even really significant. So there seems to be a bit of a reduction, but not much. At least that was in this experiment. In another experiment then in a vineyard, what we did was add that same walnut, the WS is that walnut derived biochar, but then we got also another biochar derived from pine and compared that with the control. And then it actually got even worse because obviously what you see is that we're having an increase in nitrous oxide not a decrease in nitrous oxide. In the second year, it was not as bad with that walnut-derived biochar, but with the pine, we clearly have quite a bit higher emissions of nitrous oxide. So it's a bit counter to what people had claimed and what I guess some of us were hoping for. And you see actually that it is mostly coming out of the alley. So it's where we added it, to the cover crop, and that. So in the alley, the tractor row, that's where we get most of the emissions, and it increases when you add the biochar. So in summary, across all of these systems, and I didn't show the lettuce data, but that's some of the, at the bottom there's some lettuce data too. And with, BAU basically means business as usual, so that were the systems where there was no best management practice. Others we had indeed the biochar added, or we did that integrated system in the tomatoes. And you see, if you look at the emission factors, just like Martin was showing, there's a wide variety there of emission factors. You see, you go from basically a 0.12 in that lettuce system to about 10%. In that vineyard in some years. So there's a big difference. And indeed, if you even look within the vineyard, we have, from about 0.66 to 10%. So there's a wide variety there. And it really makes me actually kind of skeptical about what the use is even of these emission factors, because clearly, they're all over the place. And if you add then the data from Martin to it, then we're going to have even more variability. So in conclusion, I would say, there are options, but there are no silver bullets. You saw it, in some systems we see a bit of a reduction, in others we see an increase with some of the best management practices. But the tomato system is a perfect example where we actually can reduce that N2O and do not have a yield penalty. So it works out pretty well. The biochar is clearly not a silver bullet as far as it goes for N2O emissions. And then I do think indeed that, simple emission factors basically fail. And so because we have under and overestimation, we have, all kinds of numbers. And so I would say, we kind of have to stay away from just multiplying, I have this many acres of tomatoes and there's an emission factor of that much, and therefore across the California, we have this much emissions coming from tomatoes. I think we should stay away from that. And with that, I just have to acknowledge the people who do really the work, namely the students, postdocs, and technicians. I'm only talking about it. They do really the work. And then the different funding agencies that have helped us with, or have get us out to do the measurements. Thank you.
Save the questions after we finish our presentations. So I just want to mention that Professor Six is going to move to Switzerland next month, and he will be a professor. Okay, I just wanted to mention that Professor Six will going to move to Switzerland next month. He will be a professor at the ETH University. I'm not familiar with the European university, but it's viewed as MIT in Europe. So a big congratulations to Dr. Six. I also would like to take this opportunity to thank Dr. Six for his tremendous contribution to our program and for taking time out of his busy schedule amid the packing to give this presentation. Let's give another round of applause to Dr. Six to wish him the best. Okay, let's now move to our last speaker, Professor Grajo. Dr. Grajo is an associate professor with the California State University, Fresno. Professor Grajo's research has focused on nutrient and water management in cropping systems. Professor Graham has been recognized by many awards for his outstanding research and mentorship to the students. Let's welcome Professor Graham.
Thank you very much, Lee. Well, first of all, before I continue, let me just acknowledge the people who actually helped in a lot of this. Dr. Kassel Sharma, Sean Ashkan, so many people down at Fresno State, and I have my grad student here, Navreet, who is actually, as Johan pointed out, actually does most of the work, or if not all the work. And Bill Salas, who is not here, but who's been collaborating with us out from New Hampshire. My talk is going to be a little bit different in the sense that we're not going to present a lot of the results per se, but over the 2 years of the project that's been funded by the CDFA, we've actually had some challenges and have been able to deal with these and kind of sort of remodify the project so that I think we're on the right track now. And what I'd like to do is highlight some of these. So basically, I'll just recall a little bit of the overall objectives in terms of what our role or our goal and kind of research that we're looking at this phase and over the next 2 years. And then I'm going to reflect a little bit on some of the sampling data that we've actually collected with the focus on one of our cotton sites out at Fresno State. And just to let you know that we're actually doing the similar type of work with primarily cotton and tomatoes. I'm going to highlight some of the data that's actually been collected that is in progress. I'm definitely not going to present any of the emission and data factors right now because those are in progress. And in addition to the ultimate goal of trying to model some of these data with the intent of getting an emission factor, we are also involved in a little bit of work that's looking at comparing two technologies, which is the Innova devices with our EPA standard static measurements. So from our perspective, the overall goal is to determine some detailed time series nitrous oxide emissions in an effort so that we can model it and ultimately quantify the amount of nitrous oxide emissions that are coming out from practices that involve a combination of crop factors, climatic factors, agronomic factors, or cultural practices. And the model that we're focusing on, and this is where the people out at New Hampshire, Bill Salas and his group comes in, is looking at the denitrification decomposition model, or the DNDC model. And this is not meant for you to actually memorize or to get too taken up in, because we've actually had some introduction about the nitrous oxide pathways that are incorporated in this model. All I want to highlight here is basically the DNDC model as presented is, simply put, a nitrogen budget combined with some climatic factors, right? Climatic factors, soil factors, vegetation, as well as cultural practices. So basically what we're trying to say is, if we have some practices that are going on out there and we can quantify these different input parameters with the intent of trying to quantify what would be the nitrous oxide emissions associated with this, then ultimately we can probably try to model that system. Now the DNDC model per se has been used extensively globally. This graph simply shows you a number of different locations in places such as Canada, parts of the US, Canada, the European nations, Australia, New Zealand, Russia, China, Japan, etc. But significantly missing on this are where the models have been actually applied to California situations. Having said that, there is now a subsequent study that's going to be looking at that. I just want to highlight that. Our ultimate goal is, if we acknowledge that there are going to be some sort of nitrous oxide emissions or flux data associated, and there's going to be variability as outlined by Johan in his piece of work, and with the recognition that we can't have a simple emission factor, it would be worthwhile if we could actually model and try to curve fit that data that we get for some sort of period, whether it's prior to the growing season, through the growing season, subsequently, maybe after harvest, and then probably the first rain, second rain, or even many other practice, as long as we could probably go. And ultimately, what we can do is try to curve fit those points, right, with whatever model, and in this case, we're trying to use the DNDC model. And then if on the x-axis we have something like time, and on the y-axis we have something like flux, which is the amount of the unit, in this case nitrous oxide emissions, per area, meter squared, per day, which is flux. And you multiply that by the time factor, which is basically integrating the area under these curves, we can then quantify or come up with some cumulative amount of, in this case, nitrous oxide that might be emitted throughout the season. Once we use that, then we go back to our emission factor, and we try to make a best guesstimate or a best estimate of what this number is, and then see how it correlates with some of the other emission factors that have been reported. In terms of the methodology that's been used, we've stuck with the other methodology that's currently being used in the other projects so that we can actually be able to share data and use this data as part of the other projects to look at data or baseline data. We are currently using the static method with the flux chamber, where we actually collect samples with syringes, then take them to the GC, and then we use our curve fitting data, etc. In terms of sampling, apart from the nitrous oxide emissions that are actually cover, or gas samples that are actually collected according to this EPA standard method, we are also collecting soil factor data, and in an effort to quantify soil moisture and water-filled pore space, etc., the carbon to nitrogen ratio, and also the nitrate and ammonium levels, soil pH, bulk density, redox potential, saturation, field capacity, and also soil temperature, with the recognition that hopefully these factors can be put into that model as, let's say, the soil input parameters, along with the crop factors. You have a list here. I'm not going to go through those, but basically what it is as recognized earlier by Martin Burgundy and Johan, it's important that we know the type of root structure, the type of cropping feature that we're going to use. And finally, climatic factors, and we're going to use these primarily from what's available on the internet, on the database. In California here, we have our California Irrigation Management Information System. So we're not recreating the entire wheel, but we're actually using data that's available. Ultimately, all this is going to be put into the model with our intent to try to come up with some sort of data. Just to give you an idea of one of the sites that we actually have on campus, here it is where we're trying to look at our cotton site, where we're trying to quantify the nitrous oxide flux with a system that actually being fertilized with urea ammonium nitrate, and then you have a comparison with the addition of a nitrification inhibitor and urease inhibitor, better known as, commercially sold as Nitrous here. Just to give you an idea of what it is like, the experimental design completely randomized, and we do have incorporated into that 3 fertilizer rates with and without the nitrification urease inhibitor. In addition, we do have one control part where we don't put any of these fertilizer. Now, just to show you what sorts of trends we're getting, notice on these graphs there are no units. I'm just trying to show you that, hey, with the kind of data that we're actually collecting, we can see if there are trends, we can see what are the averages, flux from these different systems, and here you have an example after fertilizer addition. Here you have these 7 treatments being compared, but you can see just by the error bars and the shape of the graphs, we can actually be able to quantify these. In subsequent studies and subsequent presentations, we will quantify this or do the determination to know the actual nitrous oxide emissions. In this second graph, you have an indication of where irrigation has actually influenced that amount of nitrous oxide emissions or flux. So this is where we're heading with this type of data. If you recall, I said that we're going to talk a little bit about some of the challenges and how we've improved the technique since we have this. In the first year of the studies, I think we were a little bit too ambitious. What we are trying to do is get to many sites with limited number of measurements. And what we soon realized is, hey, it's probably better that you focus on some less sites with more intense measurements. Now, bearing in mind that you only have so much money and so much student help that you can only take so many samples. But this graph is this table is being put up here just to highlight the kind of data that was actually collected in 2012. We've secured this site for 2013, so we're going to probably repeat this kind of measurement. This here just simply shows the number of number of air samples that have actually been collected and subsequently going to be analyzed to determine the nitrous oxide measurements or concentrations, and subsequently flux data. Associated with every single one of these samples or sampling events are soil samples that are actually going to give us the soil moisture content, the carbon to nitrogen ratio, the nitrate content, the ammonium content of that soil, and in addition to any yield data we'll acquire from the grower, etc., as well as the management practices. So again, we are taking an approach where it's a little bit different. We're looking now at this combination of factors, try to get what's the holistic effect of all these factors, look at the nitrous flux measurement, measure that, try to model it, then go back now and see what it is, what percentage of the actual fertilizer is applied or input. The downside with that is there's still a need to quantify the nitrous oxide pathway to know exactly where they're coming from. All right? And I recognize that, hey, that might subsequently be one of the way that we'll eventually go once we can get these numbers. But I think in this approach, we can't really say, okay, this would be, we know this management practice with these crop factors, with these climatic factors can result in this amount of emissions. The good thing about that is if we can fine-tune that model and maybe test it and calibrate the model and validate it against some measured data and hopefully test it in conditions either similar or with varying factors, we can probably get some good numbers that would be reliable, have some sort of integrity to it so we can use it. Just to let you know, as I said, with this work, we're going to continue doing it in 2013. We've secured the site. We're going to repeat this experiment. Give you another example of another cotton site. We have one where we're actually looking at the ammonia emission, the nitrous flux emissions, nitrous oxide flux emissions from the furrow system, the furrows versus the beds. Again, as highlighted here, it's going to be water in addition to fertilizer additions. It's going to be practices such as water management, practices such as soil carbon nitrogen, or changes or management practices. Hopefully, we could integrate the effect of all these in this modeling system, and that's what we're subsequently trying to do. Fortunately, on campus, just to give you a little insight of what are some of the other things we have on campus, because of the fact that we have other ongoing research involving, for example, vegetable crops. By nature, I'm the veg crop professor at Fresno State, so I do have a little bias in looking at some of these crops. And for the past 2 seasons, we've actually been able to be fortunate enough to utilize some other experiments where we've looked at fresh market tomatoes. And we had one system where we had a split plot design where we had like fertilizers well, first of all, we had irrigation, subsurface irrigation at 3 rates, 100% ET, 80% ET, and 60% ET. And in addition to that, we had a split plot design where we looked at 3 fertilizer rates, 60, 120, and 180 pounds of fertilizer. So we're looking at now the combined effect of just subsurface drip irrigation applied at 100% meeting the evapotranspiration requirement, 80%, 60%, combined with fertilizer rates. So maybe there's an interaction effect there. Maybe there's a effect where the fertilizer might be more dominant than the water application rate. But nonetheless, again, we'll be able to model these nitrous oxide emissions versus for these overall management systems. Here's an example again, this year, 2012. We've also secured that site for 2013, and hopefully we can do the same amount of measurements. And again, as I say, every single time that these events are taken, we have soil samples being taken and the subsequent measurements that we talked about. We were also fortunate enough to have an experiment where we had some open top chambers out at Fresno State. These are looking at elevated CO2. As mentioned very early in the introduction by Lee, Dr. Lee, she said, we had these 6 greenhouse gases that we need to look at. And it would be, ignorant of us not to want to look at what might be the interaction with, say, CO2 emissions versus N2O emissions. How do they interact, or, what sort of interaction you have there. In these experiments here, we had these large open-top chambers, 15 feet by 15 feet wide by 10 feet high, and open to the atmosphere, where we would actually have elevated CO2 levels pumped into some of these chambers. And we had a fresh market tomato production. My other grad student who is here is actually working just on the CO2 emissions, but we figured this would be a good opportunity to actually do some of the N2O measurements. Again, take all the subsequent data, all the similar type of data. Here's a little design for the experiment. It's a split plot design again with 4 blocks, and we were able to take, so it's completely randomized, it's statistically sound design. And here's the kind of data that we actually collected in 2012. We will be repeating that again in 2013. So long story short is that we want to continue with the work that's actually been funded by the California Department of Food and Agriculture, and here I want to take this opportunity to acknowledge their funding. And we've also subsequently used that for some leverage to get additional funding from something called the Agricultural Research Initiative, which is an on-campus state-funded project. And with that 2 sources of funding, we're going to continue to the project into at least until December 2013, where we can try to measure some of these parameters that I actually talked about, and hopefully we can look at the N2O concentrations measured in the field versus what we can actually predict, and then subsequently determine what we will call our best guess emission factor for those conditions under those agroeconomic practice, soil factors, and climatic conditions. Ultimate goal is that if these models can predict, can be calibrated and validated for these conditions, hopefully we can then extend it for maybe similar type conditions, or as we subsequently go and understand into the pathways that might affect nitrous oxide emissions combined with other laboratory and incubation studies, we can put all that into the model and ultimately fine-tune the predictions. Before closing, I just want to mention one other little piece of work that we're actually doing that we have the opportunity to do. Part of my other life was actually looking at ammonia and some nitrous oxide emissions from dairy facilities. And we've acquired through those studies our Innova devices, our photoacoustic type measuring devices, which simply put is the ability for us to quantify the amount of nitrous oxide concentrations being emitted based on the fact that these gases, or this gas, will have a difference in response to a photoacoustic signal. In other words, if you send just like you have a light wave that you can actually quantify the amount of nitrous oxide emission, if you have a sound wave, based on the attenuation of that sound wave, if you can pick it up, you can actually quantify the amount of nitrous oxide emission. Our goal in this piece of the experiment is simply to use that existing equipment, compare it with some of the numbers that we are getting from the static core method, in the hope that, hey, if we can do that and these numbers are comparable. It was interesting to see Johan showing some, either Johan or Martin showing some data with 2 different systems. Even though we may have an offset, if we see similar trends, it might be useful. The good thing about this device is it can take continuous measurements. You can set it up there. It can be analyzed readily. You can get some real-time measurements. So that's just in a nutshell where it is we're actually heading. We did do some preliminary measurements in 2012. We were quite encouraged with that, but we're going to repeat some of that data. So with that, I think I told I was given 15 minutes. I think I kind of use that hopefully to give you some insight into what's going on, and maybe at the end of 2013, we can probably give you some actual numbers that you can work with. Thank you very much.
Thank you.
We're going to take our seats now.
Okay.
Okay, we are ready to take the questions, and can I ask all the speakers to sit in front of the mic?
From here on, no, thank you.
Let's just alternate.
Yes, of course.
Yeah.
You want to start because we have so many.
Okay, maybe if we don't have immediate questions, maybe we can take care of the questions from the internet. Let's go through one of them. And this question is for Dr. Six. Thank you for your impressive work. One question about the Biochar. Did you characterize the biochar that you utilized in these studies? As you know, the quality and the impact of biochar can vary widely according to how it is produced and from what feedstock. It is actually the International Biochar Initiative developed over a 3-year process standards for the characterization of biochars. Did you characterize your biochars according to those standards? It may be that the results would change depending on the quality of the biochar applied, as well as factors such as soil moisture. For example, you indicated increased N2O emissions in year 2. Was soil moisture and or rainfall higher in that year?
Well, thank you for the question. There's no doubt indeed that the quality of the biochar is going to have an effect on what results. I thought I had pushed it. It's on? Okay, you do hear it? Okay. Anyway, so yeah, there's no doubt that the quality is going to play a role. You know, I mean, and I think indeed one of the worries that one should have about biochar is that these days almost anything that gets burned and forms something black is called biochar. I mean, I've heard of tires being burned and being sold as biochar, so obviously I don't think that's the way we want to go. At the same time, you know, we do, I mean, we actually have done some characterizations of the biochars. Sorry, I actually have not, you know, checked the standards of the International Biochar Initiative, but I can easily do that. We've characterized them basically with the conventional methods, and we see, you know, for example, if you look at the walnut versus the pine char, I mean, the walnut char has quite a bit higher surface area, has quite a bit of a higher CEC, it has a higher pH and high ash content, and all more than compared to the pine one. At the same time, though, we actually have done some greenhouse experiments with lettuce, so in pots, and where we had 12 different biochars, differing in quite a bit in quality, and with, I mean, and we saw some differences in N2O, you know, some a bit higher, some a bit lower compared to the control, but I would not say that we saw actually huge differences as far as the N2O emissions went. One thing that we have seen when we did it with the lettuce and we added the walnut biochar is that it did seem indeed the walnut biochar was increasing the soil moisture. I mean, this was now in the field. It was increasing the moisture. You know, you increase the water holding capacity actually of the soil, and that was then coinciding indeed with a bit of a higher N2O emission. So there's no doubt that the soil moisture is going to play a role. I have to admit that I don't remember now from that field study if one year was wetter than the other. I think it was, but I can't say that with 100% certainty.
Okay, any follow-up questions? Then we just, if no questions from the audience. Go ahead.
I have a question here.
Yeah.
Oh, okay.
Yeah, hi. I noticed in some of your studies there was 0 nitrogen applied, and you still had N2O emissions. So brings in the question of how do you account for that? Do you subtract that out? Background N2O emissions, transport of N2O emissions if it's next to a street that's heavily traveled, or wind. How do you incorporate all the background factors into your studies?
Yeah, I mean, as far as the background goes, so if you calculate the emission factors, you're supposed to indeed subtract the the background emissions. In certain studies, as you said, we had the 0 N, so then we could do it. In others, we actually do not have the 0 N, and so we can't correct for the background. At the same time, though, I mean, most of the time, if we do a correction, it leads indeed to an emission factor that's a little bit lower, but I would not say, you know, you're changing it hugely. I mean, you could see it also, like if you, most of the emissions that we see in the systems, I mean, it's right after you do one or another event, and if that, if your system is basically not being, impacted by the fertilizer, I mean, then the emissions are going to basically stay at that background level. So we have some background levels, but it's not like that makes up the majority of the emissions. When we're close to the road, I mean, in our chambers, actually, that does not have an impact because the chambers, I mean, we do a zero measurement. We do a measurement at time zero, which is the ambient, so which includes whatever is coming from the street. If there happens to be a street close by, it would have to be. I mean, you would have to be actually close by a highway before it would really impact it. But anyway, it's measured in the time zero sample. And then, because then we calculate our emissions based on a measurement done after 20 minutes of closure, 40 minutes of closure, and 60 minutes of closure. So that zero is actually taken out. So any impact from the street is actually taken out. So it's purely what's coming from the soil in those 60 minutes in that system.
Is that consistent with the other studies?
Yeah, everybody is using chambers, so.
But you're subtracting out background or some form of background or controlling it?
Well, the data that I've showed you where we had a zero N rate, we didn't subtract the emissions that occurred with the zero N rate from the other emissions. And the reason was because it's just like it's custom. I mean, if you compare this with a lot of studies that have been made all over the world, there's actually a debate going on because many people did not measure a zero nitrogen N rate of N2O emissions. And so some people argue that it's hard then to compare the data. And I think we're open by showing both the emissions that occur with zero N input and with the N inputs, and then it can be subtracted if you want to.
Yeah, and in my case, the one with the zero input, we're going to have that data. And now that you mention it, I think it would be worthwhile minusing that data, that N emissions from zero. In the case where you're comparing like the beds versus the furrows, we're looking at a relative comparison. So I think in that case, you're assuming that the N emissions from no fertilizer is going to be the same.
Thank you.
Yeah, to pursue on this, I think, zero N rate means zero N for this growing season, but obviously the soil still contains nitrogen from others. And I think it brings me to the case of alfalfa. I don't believe alfalfa receives any nitrogen fertilization, right? It still has a very high emission factor. And I'd like to see if any of you want to elaborate on where is that nitrogen coming from, and are there any maybe management possible there?
Okay, yeah, I can answer this. So yeah, what I showed is that the older stand had the higher emissions than the younger stand, and that is actually also been shown in another study in Canada. And neither those researchers nor us, we had a good explanation, except that we think that it's turnover of organic matter, root turnover in the older stand. There is just more mineralization of nitrogen going on. In terms of reducing emissions, we will have starting experiments with actually drip irrigated alfalfa, because we think that may be a good bet to reduce the emissions.
And one more comment on that based on the work that's been presented. Obviously, we think these nitrous oxide emissions are mediated by moisture. And in natural conditions or whatever, these microbes are working nonstop. And I think definitely there is now a need. this surely emphasizes the fact that we need to look more into that pathway. Whether it's a legume versus a cereal crop, it's worthwhile examining. But good question, yeah.
Yeah. We can take another one.
I don't have the slides in front of me, so I apologize if this is a dumb question. Going back to the alfalfa emission slides earlier on, I think in your presentation, the amount that they were emitting was higher than some of the other crops. Was that expressed on a percentage basis, though, as opposed to a mass unit basis? In other words, are they emitting massively more on a surface area basis than the other crops, or is it a higher percentage of N2O versus how much nitrogen is actually applied? Because I would think as a nitrogen-fixing crop that they would not have as much nitrogen applied to the crop overall on an area basis, say, compared to something like corn or tomatoes.
Yes, there was actually very little nitrogen applied. It's only every other year this grower applies. Ammonium phosphate is a very low dose, something like 20 kilos, and that's only because of the phosphorus that he's applying. So there's no N application. But to answer your question, the data that I showed, these were absolute values, kilograms N2O, N per hectare, and it compares with the other values that I showed, like tomato, 1 to 2 kilos or something like that. So they were higher in the older stand. In the young stand, it was comparable to the other crops, like tomato, for example.
Okay, we can take another question here. This is for Dr. Berger. Dr. Berger mentioned the nitrogen additions, soil moisture, and the cropping systems as controllable factors in nitrous oxide emissions. The slide also showed the soil carbon texture and the pH, which can also be controlled. So is soil quality a significant factor as well? What would be the highest priorities for further research on agriculture and reactive nitrogen? So what kind of factors we can control besides irrigation, the type of crops and fertilizers? And also here, maybe, soil carbon texture and the pH. Do you think soil quality is a significant factor?
Well, first we need to know how we define soil quality. And I think as far as the data that I showed is we showed two different soils with different management. One had a cover crop for 20 years. These were our cover crop plots, and the other not. But they were exactly on the same soil type, and it looked like we did have an effect in this case of, in some years, maybe a tendency for a little bit higher emissions. We know that low pH definitely it can enhance N2O emissions, and then we can do something about it. What would be the highest priority for research in agriculture and reactive nitrogen? I think it's very clear that we have on the planet we've about doubled the amount of reactive nitrogen, so we want to minimize putting more reactive nitrogen there. And I think the way to do that, I think the highest priority will be to increase nitrogen use efficiency, because that will have the potential to lower emissions and also has other benefits, like reduced nitrate leaching, for example. Yeah, I think that would be the highest priority.
Okay, we can go move to the next question. This is for the researchers, but I think probably Dr. Six can take that. Can you discuss the instrumentation you are using for measuring N2O? Is the same instrument or analyzer used for chamber measurements and the eddy covalence measurements?
So in our lab, and I mean in Martin's also, we are using just a regular GC, gas chromatograph, for measuring the N2O, because what we're basically taking gas samples out from the field, put them in little vials, and then we bring them in and into the lab and measure the N2O on the regular GC setup for greenhouse gas measurements. Dr. Garua, though, is using the ANOVA, which is another instrument. It, works on a bit of a different basis, but cross comparisons have been done between these instruments, and that's, there's no real bias there from one instrument to the other. Once you go over to eddy covariance, though, we obviously have not done any eddy covariance for N2O. There are some developments happening at the moment to do that in eddy covariance. At the moment, though, there are no instruments that can do it as quickly as they can do it for the CO2 and the methane. But we're getting better. There's several companies that are, as far as I know, actually lovely competing with each other to get the first and the best instrument out there. And so I think indeed in the future we will probably be able to do eddy covariance for N2O, or at least within a few minutes time frame. At least that's how it's looking like. But that's not what we're using for the chamber measurements at this point.
Question for Dr. Berger. You mentioned that in one of your experiments there was some soil analysis before adding more nitrogen to the crop. Is that correct? And adjusting the amount of nitrogen allowed for higher nitrogen use efficiency. So could you, any of you, comment on what's the potential in California agriculture to use more of that type of method to adjust the amount of nitrogen and, increase the efficiency, reduce the N2 emissions, and is the potential better in crops like lettuce or field crops or, row crops? So.
Well, I think to some degree this is being done by some farmers, but I think not by all the farmers. And the people who know most about these practices are our extension specialists. And if I listen to them, they think there is still a lot of potential to increase nitrogen use efficiency. For example, especially, that was just an example in that one area in Salinas where soil testing reduced the fertilizer input by 50%, but didn't really affect the yield. But it was just an example, really, so I think there's definitely potential, but I can't put any numbers on it.
I just want to add something on that comment. I fully support the idea that there is a need to do these pre-soil testing, and if it's just a matter of source control, because the literature has clearly shown that there is increased emissions with increased nitrogen applications. But it brings back to an earlier question. If we have to identify if we have to identify what would be a major research goal, I think it would have to be a collaborative effort or a holistic effort to look at addressing the nitrogen cycle. We can't just look at what might mitigate nitrous oxide emissions and what might be happening to nitrate leaching or ammonia emissions or one or the other. And that in itself is, that's what keeps us in our career, because it's really complicated. But if there's a real goal, and we could probably maybe quantify all these different components in a given study, I think that would be one way to actually, go in terms of top priority for agriculture.
Dr. Gurhu,
Yeah.
we've been fairly critical in the past of the use of your field analyzer, i.e. ANOVA, that really has some inherent over-calculating, under-calculating interferences, both positive and negative, at looking at a lot of compounds, specifically when you guys were doing some of the VOC research. Yeah. How is this going to be any different? And is this potentially N2O a compound that is also going to have a tremendous amount of interferences like we saw with VOCs?
Yeah, that's a very good question. Yeah, I know there's been some complications with that. And the reason why I decided to pursue it is I have another colleague out in Iowa who's actually been looking at the ANOVA, and he seems to think that it's worthwhile. At this stage, we'll definitely have to address that. If we see that there is great discrepancy within what we're actually getting from the ANOVA, and we can't correlate it with what we're getting from the static method. Maybe these inherent errors might be masked by the fact that we're getting a fixed number and it might be consistent. But good point. I know with the VOCs there were a lot of inherent, as you call it, overlaps and interferences. I'm not sure, but the reason why I suggested that I look at it is if it could work and we can get some sort of correlation, it gives us that opportunity to really measure real time, and a lot more time saving. But I might just come back next year and say, too many differences, and we might just have to scrap it. But thanks for pointing that out. Yeah.
Okay, the next question, that's for Dr. Six. Dr. Six, you cite the data from ARB's baseline greenhouse gas emissions for agriculture with nitrous oxide being 51%. Based on the research done by the groups and others, for example, Dr. Smart in UC Davis. Do you think this emission source will shift as ARB's analysis was completed before California-specific data was available, despite your doubts about the emission factors? So there's two more. Maybe you want to address the first one?
I think there is potential that it would change in the sense that I know when we started, about, what is it now, 6 years ago or something like that, with the different projects, we were expecting indeed that we, if anything, that we would be always a little bit higher above the 1%, that is generally being used across the world, what IPCC is using. Because we thought, okay, we're an irrigated system, so there's quite a bit of moisture. We know we're adding quite a bit of nitrogen. These systems are, kind of prone almost to have, denitrification happening. In contrast, though, as you can see, if you look across all the numbers, we do definitely have some numbers that are quite high, but we do also have quite a few numbers that are below the 1%. And I would say on the average, we are probably more below the 1%. And I know, in many ways, what we have started seeing, from the data is that indeed we have irrigated systems, but most of the time, actually, our nitrous oxide does seem to come from nitrification, not so much from denitrification. And when the irrigation is happening, we do get denitrification, but luckily it seems to be pushed all the way, and so the N goes all the way to the dinitrogen, and we're not having as much N2O coming out. But at the same time, you could see also, there were systems that all of a sudden had 10%. So I think we can for sure, there's at certain moments, there's a lot of emissions that are coming out. So if I would have to bet on it, I don't think I would, if this is going to change the numbers. But at the same time, I do think that we are a bit lower than what most people would have expected.
Okay, well, I think probably this illustrates the modeling, the role of modeling can play. So I think it's harder to say it's below or above because we have some above and significantly, and we have a lot of low emission factors. So we hope the modeling project we are doing right now can give us some more definite answer. So at this point, it's harder to say. So next question is also for Dr. Six. For the almond orchard, what was the total amount of nitrogen applied over the growing season? And
228 kilograms per hectare per year.
Okay, the next is, have you been able to compare your results in almonds with vineyards with data from David Smarts and that has done N2 emissions in both crops?
Well, I mean, this is Gabriel, obviously, who's asking this. No surprise. And she has asked me this already many times, and I guess I will have to answer the same question again. No, we have not compared. The day I can get Dave Smart to sit next to me and show his data, it will happen. Well, he better get his act together.
Okay, and next question for Dr. Graho. And can you talk more about what kind of nitrogen inhibitors you have been trying? What is it? What rates? How applied? What's the cost? And other possible impacts of their use to the agronomic system?
Okay, as I indicated on the current study, we're just looking at one nitrogen inhibitor. It's a proposedly nitrification/urease inhibitor. It's being applied at a rate that's recommended by the commercial rate, and I can't remember the exact rate right now, but I can definitely send that to the individual. It goes by the trade name Nitrous. It's the experiment is either with or without the product. It's applied by mixing it with the urea ammonium nitrate, which is applied at a time of application. The cost per acre would be whatever is the cost per unit of the material plus whatever inherent cost in applying the rest of fertilizer. Other possible impacts? Good question. Brings back my wish about trying to measure all these components of the nitrogen cycle. Maybe I might be cutting back on some of the potential of breaking down the nitrates to that pathway that referred to by Johan, and subsequently I might be leaching some of that nitrate. So exactly what are some of the other impacts? There is definitely a need to look at that. We hope that some of the soil data that we are collecting would probably answer some of that. Also, it might be looking, in terms of a point of agronomic value, it might be worthwhile looking at the nitrate levels in the plant uptake and subsequent yield data. So short answer to the question, yes, there will be some other impacts, and we'll definitely have to look at soil parameters, crop parameters, and solution or water parameters to see whether we might be mitigating one problem and adversely affecting another. And so good question in the sense that I think we've just identified exactly what we need to look at or what parameters we need to measure for this component of the study. Okay, thanks.
This question is for Dr. Berger. If you could help me understand a little bit, I think I'm just not grasping some of the things you said. In terms of the percentage of total greenhouse gas emissions of a tomato field as N2O, the percentage of total emissions as N2O, it seems like your emissions factor is indicating that the N2O emissions were higher than perhaps initially expected at 1.5% as opposed to, say, 1%. And yet it seemed like you were saying the N2O emissions were anywhere from 30% to 50% of total greenhouse gas emissions. So am I correct in saying that that was your understanding of the percentage of total greenhouse gases that were N2O? Or did I misunderstand?
Okay, yeah, sorry about the confusion. So the first one is the emission factor, which is the percentage of N of the fertilizer that is emitted as N2O, and the default factor is 1%, and so we are a little bit off, and below that between 0.5% to maybe 2% in the studies I've shown. The total greenhouse gas emissions, that is going beyond this analysis, and here we just looked at 4 different components: the emissions from fuel, the power farm equipment, water, energy, and then the direct emissions, and then also we included the emissions from fertilizer production. And so when I refer to 30 to 50%, it's just that was the direct emissions of this. So the entire greenhouse gas budget then would be 100%, and then so between 30 to 50% are the direct emissions of these 4 components. So it's really 2 quite different analyses.
Thank you. I just wanted to confirm that, because when I looked at the bar chart, the direct N2O emissions generally looked like less than 30%, just at my guesstimation. So I wanted to confirm that it was 30 to 50% that you were finding when you looked at those 4 components.
Well, we have the graphs. We can exactly calculate it. Like yeah, I think the answer is in the graphs, and the graphs will be posted. So,
okay.
Okay, this question is also for Dr. Berger. Dr. Berger said his studies had shown that drip irrigation definitely reduced N2O emissions compared to furrow irrigation. Is this only true for tomato? Is it also true for lettuce, wheat, and alfalfa? It wasn't clear that his study compared furrow versus drip irrigation in lettuce, wheat, or alfalfa. So I'm wondering, how can he draw such a widespread conclusion solely from the tomato data?
yeah, I think it wasn't meant to be a totally widespread conclusion, because I referred to the tomato, but the tomatoes are such a very nice study, because both Johan Six's study showed a drastic reduction with drip irrigation, and we also showed it in different systems, with cover crop, without cover crop, and it was very consistent. And so we think actually it has big potential. And in lettuce, we have now a study where we are formally making a formal comparison between sprinkler irrigation and drip irrigation to demonstrate that. We suppose so, because our lettuce data where we use drip were quite low. And I already said that we also do it in alfalfa. And for wheat, it's different, because wheat is grown in the winter. It's a rain-fed crop, so we can't really manipulate the water there. And yeah, drip irrigation has potential. It also can increase yields. That's why people try it now for other crops, even corn sometimes. And if it can increase yield, then also and reduce the N2O emissions, then it's really even a win-win situation, because then the N2O emissions per unit yield will be lower too. So these studies are still ongoing.
Okay, this is the last question. And this is for any of the researchers. Based on your experience and what you have read, do you have any suggestions of what where to focus the use of sources of organic matter. That includes cover crops, compost, composted manure, etc. within the different agrosystems. Some think that their use would reduce N2O emissions, but the data you presented shows mixed results. Nitrogen fixer versus non-nitrogen fixer. That's alfalfa versus other crops. And their timing, location, types that should be looked at more closely for reducing N2O or exhibiting N2O emissions, for reducing or increase N2O emissions, or if used, what practices should be considered to minimize N2O emissions while maximizing nitrogen available to the crop.
Okay, I'll split it up in a few different questions, I guess, and answers. So the first thing is indeed, if you look, as far as the reductions with N2O emissions based on the use of cover crop compost or composted manure, it's correct that indeed sometimes it reduces emissions, sometimes it does not reduce emissions. I mean, we showed indeed with the cover crop, if it's a nitrogen fixing cover crop, I mean, it makes sense, you know, you are loading up the system with nitrogen, and so there is definitely potential for nitrous oxide emissions to be happening. Meanwhile, you know, if you look in systems where the cover crop is not a leguminous one, then we actually do see a reduction in N2O emissions. You know, I mean, obviously that cover crop is going to be taking up some of that residual nitrogen that otherwise would be available to the microbes, and so it could be potentially coming out as N2O. If now it goes up into the plant, then you know, you have a reduction in N2O emissions, and once it gets mowed and plowed back in, there might be a little bit of a spike in N2O emissions because of the nitrogen there, but most of the time we see then also an immobilization, and so then the N2O emissions are again not too high. So I think there's actually potential when we talk about cover crops to do mixed cover crops, so where we actually combine leguminous ones with non-leguminous cover crops in order to have a better balance. And it probably would actually also help with nitrogen use efficiency. We've actually done some studies where we mixed different cover crops, and we found that you actually increased the nitrogen fixation, and more of that nitrogen was actually being taken up into the corn. So I think it's a matter of playing you know, with your different kinds of cover crops and how to manage them. When it comes to manure, I think, I mean, in general, we know if you add it as a slurry, then you're increasing the nitrous oxide emissions. It's quite a bit higher than the 1%. I mean, we're sitting most of the time actually at about 1.5%. Once if it's the solid manure or the composted, then it seems like we're kind of at the same, if anything, a little bit lower as far as N2O emissions go. So I think there, you know, you can, I mean, we can add it, but just don't add it as a wet slurry, because then you're just going to have high emissions.
One more question.
I don't think it's a matter of really defining, you know, which agronomic system. I mean, in most systems, there's potential of cover crops. I mean, we're in California, so, you know, cover crop is most, I mean, you don't want to do it in the Great Plains because obviously you don't have enough moisture. But here, in our irrigated systems, I think it's not really crop dependent if you can use a cover crop, yes or no. It's more easily to integrate it with certain crops, but there's not really much differences. So I think it's more of an issue. Okay, I mean, we obviously have a lot of manure in California, and there's going to have to be something done with that. And so we probably have to just figure out then the best way of getting rid of all that manure. And so I don't think you're going to have to be, I mean, you're not going to start adding manure because of N2O emissions. You're going to start adding it because you just have shitloads of it. that's going to be the reason. And as far as timing, location, I mean, those all come back to the nitrogen use efficiency. I think again there, when we're managing the fertilizer, I mean, we're not going to manage it purely because of nitrous oxide emissions. I mean, there's many other reasons of why you would manage, these nutrients in a correct way. Luckily, though, the more you do it in a correct way, the more potential you also have for N2O emissions to go down. There's not a direct relationship between nitrogen use efficiency and nitrous oxide emissions, but if you increase your nitrogen use efficiency in one or another way, there is potential that you also have N2O emissions reduced. So I would say, if you look at it from a holistic standpoint on how we're going to deal with this within agriculture, nitrous oxide is one to look at, but it's not the only factor. And it's quite often probably not the dominant factor that you're going to be making decisions on. I hope Gabriel is satisfied with the answer. If not, you should email. I'm sure some of you have, that you can get immediately an email from her.
This is kind of an ask for the three panelists. Those of you that have referenced the static chamber use in your research methodologies, are you using that term? In reality, the term is actually the US EPA chamber method?
Mm-hmm.
Or is that one and the same?
That's one and the same.
Okay, so you're using kind of the wrong terminology for what it actually is.
No, I mean, it's just the different words that we use for the same technology.
Okay.
Yeah. And just to let you know.
Yeah, it's all the same technology. I mean, it's the basic same thing that you just put down a chamber that's static, standing there. And then you just let the gases accumulate in that chamber and you measure it at different times.
So in your SOPs that were approved prior to funding for these, did you guys provide the field use methodologies for this being used in the field?
I mean, they're the standard methods that basically any researcher has up to now for N2O has been doing it based on chambers. And then there's just a few people that have tried, with going towards more of the eddy covariance, because obviously once we can go over to that methodology, we're going to have much more continuous measurements and at a wider scale. And as you could see, one of the issues that we're having with the N2O is that we have quite a bit of temporal and spatial variability. And so if you do it all with chambers about this size and just for an hour accumulating, I mean, obviously you're missing quite a bit.
Yes.
So the ideal would be if you could do it in eddy covariance mode and just have a continuous measurement being done. But we're just not there as far as equipment goes. We can do that for CO2. We can do it for methane. But for N2O, we just don't have that methodology. So there's more and more a movement toward that eddy covariance mode and going away from the chambers. But up till now, everybody in the country that has measured N2O has basically done it with a static chamber or whatever you call it. It's that same methodology.
Okay, I'll be specific. The US EPA dynamic chamber.
Okay, that's the only difference there is that they actually, like Dave was doing, is that then you hook it up to a continuous flow. And so then you're having the flow continuously going between the chamber and your measurement.
That is the
EPA
approved method, though.
I mean, both are approved. GraceNet,
GraceNet.
if you look at the GraceNet, that's like the standard for N2O measurements. They go with static and then also suggest that you can do the dynamic.
So can you maybe provide to Dr. Lee where in your research proposal it actually has the methodology that you're going to be using?
There was all in, we provided it in there. And we actually did talk in the one, well, not to the ARB, but in the one to the CEC. We also talked about, doing some, and we did some measurements more in eddy covariance mode, not pure eddy covariance mode, but that was all described in
in the proposals.
Okay.
Yeah.
So that was my ask, if you guys could provide that maybe to Dr. Lee and she could
I mean,
disseminate it
the
out to the group.
proposals are actually readily available on the web. Anybody can get to it. They're right there.
Will these presentations be available on the web?
As far as I know, yes.
Okay, so I think, we have, if you have more questions, you can, email us, any of us, and we will follow up. So thank you for coming to the seminar. So I think thank you very much.
Good job.